Okay, so let's quickly summarize the linear model for classification, i.e. the perceptron. But now we have this beautiful theory of generalization, this VC theory, to back us up. Okay, so the linear model for classification. Okay, i.e. the perceptron. Okay, and the hypothesis set H, now I'll call it H sublinear, is hypotheses of the form H of X is equal to sine of W transpose X, where W is in R to the D plus 1. Okay, and D plus 1, remember, because X is this augmented input vector, augmented by 1. Okay, so what is there to say? Well, first, 1. We proved, or you proved in the exercises, and we generally discussed that the linear model, the perceptron in D dimensions, is broken, okay, and has a VC dimension of D plus 1. So the VC dimension dVC is equal to D plus 1. Now you might think, well, what does that mean? That immediately places this hypothesis set into the set of good hypothesis sets, the ones with which we can learn, it's feasible to learn, okay, by establishing the link between E in and E out, at least for large enough n with high probability. Okay. So we have that E in, E out is linked to E in, and this is for G, okay, plus an error bar, okay, and when you plug in this VC dimension, the error bar has an order of magnitude which is the square root of D log n over n. Okay. This would have been dVC, the VC dimension, but the VC dimension is order of D. So that's nice. Okay, roughly speaking, it says that, if you have a number of data points that's much, much larger than the VC dimension, and typically about 10 times larger suffices in practice, then you've got this link between E in and E out. Fantastic. Okay, so that's the first step of learning. First step of learning accomplished. Check mark. Okay. And, so you're approaching a machine learning problem and you're picking your hypothesis set. So this is the kind of, workflow that you have to implement. You have to check, have I accomplished the first step of learning? In other words, is my error bar between E in and E out small enough? And that depends on the hypothesis set you pick, i.e. its VC dimension, and the number of data points you have. So you can perform this check. Okay? And just because we're doing it with the linear model doesn't mean you cannot do it with any other model, any other hypothesis set for which, somebody else may have done all the hard work and computed the VC dimension for you. Okay. All right. Now, what about the second step of learning? Okay, what about E in? Okay, and that's where we had the perceptron learning algorithm. Remember, we have this perceptron learning algorithm, and we have this theorem. If the data is separable, okay, then you can get E in of G equal to 0. So that's what it means for the data to be separable. Okay, and if the data is separable, you can get E in of G equal to 0, and the perceptron learning algorithm will accomplish this. And perceptron learning algorithm will accomplish this. And you prove this as a theorem. Okay, so that's a theorem. So not only is it possible to get E in of G0, but you can find that hypothesis set from this uncountably large hypothesis set. You can find that final hypothesis that accomplishes the second step. So the second step of learning, accomplished. Check mark. Oh, but you're all probably shouting, wait. Okay, a fundamental assumption in this theorem that got E in of G equal to 0 in finite time was that the data is separable. So, immediate questions. What if the data is not separable? What if the data is not separable? question mark. And, okay, for the general case where the data is not separable, okay, how do you ensure that it's possible to get E in of G close to 0? How do you ensure, quote unquote, E in of G approximately equal to 0? So, two issues we have to address. Now, the first issue, what do you do if the data is not separable? That's very easy for us to address. Okay? And, you basically have to update the perceptron learning algorithm so that it can tolerate error. Okay? And that algorithm we're going to call the pocket algorithm. Okay? And then, how do you ensure E in of G is close to 0? So this algorithm that tolerates error, does it necessarily go to the minimum E in that is available within this hypothesis set? No. Okay, so you might, so how do you ensure E in close to 0? There's an algorithmic side to that. Okay, so the algorithmic side, which is for non-separable data, how do we get to the best hypothesis in this set? It turns out that falls within this class of computational problems which are very, very, very hard. They are what are called NP hard, not only NP hard, but NP hard to approximate. You can't even approximately get to the minimum. So then it turns out that this simple update to the perceptron learning algorithm is quite good. It's almost the best you can do. Okay? But then the issue becomes, well, no, it's not just an algorithmic issue of trying to find the hypothesis in here that has minimum error. There's also sort of this attainability issue. Maybe there is no hypothesis in here with a small enough E in. In other words, maybe this hypothesis set is deficient, in being able to approximate the target function. Okay, and that's where you have to think a little bit. That's where the expert comes in, both the machine learning expert and the expert in the domain. And you've got to think a little bit, how do I solve this problem? And what it ultimately boils down to is you need to pick good features. Okay? And we're going to discuss both of these, today. So, and all kinds of exciting things planned today. We're going to try the projector. We're going to see data. Okay, so the first order of business, turn on the projector. Okay, so here's some non-separable data. Think age, income. The red X's are applicants who defaulted on credit. The blue circles are applicants who paid off their credit. We'd like to separate them with a line. You cannot, because this data is not separable. So here, this blue circle is an error, because this line says red. That red X is an error, because the line says blue. Okay. Now, PLA. What will PLA do? So let me remind you of the update rule for PLA. It says that you're at some weights W at time T. Find a misclassified point X star, and multiply that by the y in the data, y star, okay, and update the weight to W of t plus W star, or plus y star X star, and we call this W of t plus y. Okay, so that's the update rule for the PLA, and at all iterations, you will always have a misclassified point, so it'll go on forever. Okay, so we need to be able to tolerate this error, and the fix is very, very simple. It's what we call the pocket algorithm. Okay, and it's so simple you might think, wow, anyone could have thought of that. Does it really work? Okay, and it's pretty much as good as anything. Okay, so first, what's the algorithm? The algorithm is run the PLA. Okay, and, at each step in the PLA algorithm, you take your new weights and you compute E in. You evaluate those weights. Okay, and if the in-sample error for those weights is the best you've seen so far, you put it in your pocket. You store it. You say, that's the best I've seen so far. Now you do the next iteration. You get a new set of weights. Okay, you compute E in for this new set of weights. Okay, compare it with what's in your pocket. If it's better, throw out what's in your pocket and put the new set of weights, and keep doing this. So in this way, you are continuously updating the weights that are in your pocket to the weights that achieve the minimum so far. Okay, and that's a reasonably costly process, because you have to compute the in-sample error for every new set of weights that you get, and then compare that and keep the minimum. Okay. But if you want to be able to tolerate error, well, then here's a very simple way to do so. Okay. And it's guaranteed that the weights that are in your pocket can only get better as you do more and more iterations. Okay. So unlike the perceptron learning algorithm, which, if the data is separable, will stop, the PLA will go on forever, because the pocket algorithm will go on forever because PLA goes on forever. So you have to decide when to stop. 10,000 iterations, a million, a billion, a trillion. Okay. Maybe 1 million, depends on the dimensionality of the data and the size of the data set. Because remember, at each step you perform an update. This takes a running time that's proportional to the dimensionality, and then you have to compute E in, which is a running time that's proportional to the dimensionality times the number of data points. Okay. So computationally, pocket algorithm adds a lot of overhead on PLA, but it allows you to tolerate error. Are there better algorithms? Well, as I mentioned before, finding the hypothesis in this set, i.e. finding the weights which minimize the in-sample error, very hard problem. Computationally hard. We can theoretically formalize that, okay, but let's not. Okay. It just means that it's a very hard problem, and people are working all the time. Most of the effort is, we have to run the PLA because the PLA is always improving the weights. Okay? But we can choose where the PLA starts. And if we can improve the starting point, let's say not starting at a random set of weights, but at a set of weights that, is produced by an algorithm that, can be efficiently run and produces a set of weights that are in some sense good, then we start from a good set of weights, and then the pocket algorithm improves those weights. And so there are methods that, improve the starting point based on, linear regression, logistic regression, linear blah, 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 blah. We'll see some of these. Okay? So the pocket algorithm is the way to update is the way that we're going to update the perceptron learning algorithm to tolerate error. Okay? That just means we can tolerate error. It doesn't mean that we get to a good E in. Okay? So let's talk about how we get to a good E in. How do we get to a good in-sample error? Okay? And in order to address that, we're going to introduce the data set that we're going to use for the semester. So wow, yay, we're going to see some data today. So let me erase.